Welcome to Tech Talk. I am Engineer Sherwin Sarmiento from Global Estate Resorts Incorporated. I will be discussing gable frame analysis and design, steel design with tension-only elements, and wind load on an open structure. The contents of my discussion are the following: project introduction, design criteria and parameters, applying wind loads to an open structure, steel optimal design, tension-only elements. The location of the project is in Palacio Real, Laguna. This type of structure is a steel gable frame and the dimension is 34 by 23.6 meters by 8.13 meters high. As you can see, this development is still undergoing. The codes and standards that I used for the design and analysis was the NSCP C101-10 National Structural Code of the Philippines, Volume 1, 6th edition. For the steel design, I used the American Institute of Steel Construction Incorporated, 13th edition. For the foundation and for the pedestal, I used the ACI 318-08 metric version of the American Concrete Institute Building Code requirements for structural concrete. The materials that I used in the design of the gable frame is for the concrete compressive strength I used 21 megapascal, and for the structural steel yield strength I used 248 megapascal. For gravity loads, for the self-weight, unit weight of the concrete was used is 24 kilonewton per meter cube. The unit weight for structural steel that was used is 77.0 kilonewton per meter cube. Other gravity loads such as the superimposed dead loads I used for mechanical, electrical, and plumbing. I assumed a 0.55 kilonewton per meter square. For tenory and other miscellaneous connections, I assumed a 0.50 kilonewton meter square. And for the purlins, I assumed the weight was 0.055 to 0.1 kilonewton per meter. For the roof live load, since the tributary area per rafter is more than 60 meters square and the slope of the roof is around 10 degrees, I was able to use so in my previous design method, I used to divide the pressure by the tributary width of the purlins or the rafter and apply it manually. I would apply manually here half the tributary width and the full tributary width on this area. In MIDAS Gen, we can do that in a simple step by applying floor loads to the area of the rafter, and it would apply it, or it would calculate it by itself. As you can see here, it shows that it's only 3.6 on the downward position, but actually it's overlapping on these areas. To show that it is overlapping, I did a simple analysis already, and you can see for this section here, which is this one, it is twice the amount of shear compared to the outer one. Also in MIDAS Gen, we are allowed to also ready model or input the purling width, and it will also calculate that by itself. So with that, we use a one-way distribution, and we apply we input the loads that we want to apply on the purlins or the roof or any member for that matter, and we apply it like this. It looks like this because Gen is calculating it like this. It's the length times the spacing times the half of the tributary area times the pressure. So it comes out the same, except for difference depending on the weight of the sub-beam. So let me show you how it's done. As you can see here, I've already imported the module file. This actually already has the connections, so I'm just going to show you how I add the loads. For this section here, MIDAS Gen cannot do floor load, so what I do is I do a technique. I put members here with the stiffness that's very low, so that it does not transfer loads. So this is how I first make a new section. I make a section that is null, or whatever you want to call it, and the stiffness is so very small that it's not able to transfer any loads. So with that section I will be applying it here and here. So let's apply that section now. I can apply it in direct, and MIDAS will automatically cut it into separate sections already. So after doing that, I'm going to apply the loads. So I've already defined the floor load, roof, and superimposed dead load as a negative 1.05, and the roof lab load negative 0.6, as I said earlier. I would add, but since it's already created, so, and now I assign floor loads. Since this is going to be a one-way distribution going that direction, I will pick a one-way distribution, and this is around 12 meters. So it's around 12 meters, and the purlin is going to be spaced at, or was spaced at 500 on center. So there is going to be 12 purlins here, 12 purlins here, and 2 purlins on this section. So, and the self weight of the purlin is 0.055 kilonewton per meter. Sorry, let's do it this way. Yeah. As you can see, this method is quicker than picking different members and applying it one by one. So this cuts the time to a substantial amount. To here. If you don't add this null section for cantilever sections, it will not apply it. It will say that it's cantilever and it will not apply it. So this method of applying a non or low stiffness member helps really well with this method. So there, I'm finished applying the roof dead loads, live loads, and now I can go to the next. So for the seismic analysis, this is what I used for the base shear. I'm not going to be talking about seismic analysis. I'm actually only using seismic so that I can add it in the computation of the finding for the members. So this is all the input. I used a 4.0 seismic factor since the Philippines only has 2 seismic zones. Most of it is zone 4. From the soil type that the geotechnical gave me, that the soil was SC. The near source factor that I used was 1 for both NA and NV. And I also used 8 for the ductility coefficient. But in UBC it specifies 8.5, but since I'm using the NSCP, I used 8. So I'm going to apply that also. So applying seismic loads, I'll be using the UBC 97. The soil is SC, zone 4, and it's more than 15 kilometers away from the nearest fault line. Ductility coefficient is 8. And I'll be choosing for the method A, I'll be choosing one since it's a steel structure. And I'll press apply. Oh, so this is 0. And for the Y direction, it's the same, except change this to 0 and the Y direction is 1. Apply. Also, I will be checking the fundamental period of the structure by method B using eigenvalue. I'll just put arbitrary number 15. And then I will be running this to check the fundamental period of the structure. So I'm not going to be selecting any of this because I'm just interested in checking the fundamental period. So my major one is for the X is the third mode, and for the major for the Y is the first mode. So that is 61. So that's 0.28784x. So I did a screenshot of the fundamental the mode acceleration. So along X it was 0.2838. Oops, what happened here? So 32878. For the Y, which is this one, so it's 0.8614. Mode 1. Okay. We also modify the EQY. So this is 0.2878. 8614. 86. Okay. So now I'm done applying the seismic load. I will be now going to the next. Moving on. So for wind load, applying wind loads. This picture tells or shows how an engineer is the one that has to design for the wind, and everyone else is having fun. Okay, moving on. The pressure that MIDAS Gen is using is this one, this formula right here. You can also find it in the NSCP. Since it's in zone 2, the structure is in zone 2, I use 200 kilometers per hour wind. Gen also looks at the structure when you apply a wind load. It looks at it as a whole or enclosed structure. So when it's an open structure, you have to do edit the wind load and add a force opposite to the direction of the wind to make the wind force correct, depending on how the structure is or depending how open or semi-enclosed it is. So Jen, right now at the moment, Jen is looking at this as an enclosed structure here, fully enclosed. So actually this structure is open. It's open here. Here each bay has opening, and the only wind that's acting on the structure will be on this area plus the roof. So let's add the wind load. So it is 200 kilometers per hour. 61 to 2 miles per hour. It's an exposure B. And the gas effect factor. So, right, actually for this one it's 0. It's because though this section here, it tapers to a point. So Jet cannot see that. So we have to input it manually. So it's 34 meters along the X, and this is 23.6 along the Y. So calculate. So since we are adding the load along the X, this is 0, and we'll apply. And for Y, same thing. Set this is 0, and this is 1. Okay. So what we're gonna have to do is apply opposite force to counter this force here, as it is very economical or too large considering the fact that this is open. So here I have an Excel spreadsheet that I've already done. What I'm going to do is I'm going to input the lengths here, and I will copy the pressure from Gen, and I will get a force here and I'll apply it on the opposite direction. So this is 23.6, and Y is 34, and then the Y prime is the number of columns times the width of the column. So it is 6 columns and the width per column is 0.3. So this width is actually the width that the pressure is acting on the real pressure that is acting on instead of 34 meters. The height of the structure is 8.13. And the height of the column is 5.95. The height of the roof is the height of the structure minus the height of the column. So then get the pressure along the x direction. So that is 1.1875. Same for top of column. So as you can see, for the top of the column, the net force is 157. So the net force is 157. So, and we need to apply an opposite force to counter that, which is this one here. This one is the pressure below times the actual width of the wind that's going to be actual width of the wind that's acting, and times the pressure, sorry, and so we minus that and we get this value here. This value here is what we have to apply at the opposite direction to get the actual or the real wind that's applied on the structure. 107.62. So we add here, and it will be acting on the top of the column in the opposite direction. So that direction is along x 107.62. So now that we added, this is the correct pressure. This is the correct story force that's supposed to be acting at the top of the column. Now for the wind along Y, also looking at it as a closed structure. So what we're going to do is get this area here and this area here, and we're going to apply it this way. So for the roof part, for only this area, and there's zero area here, so this is the only area that's going to be acting for this point. And for the top of the column, which is this section, this area and this area is going to be acting at here. So we're gonna put the pressure here that Jen calculates, and we're gonna compute the area, and after that we're gonna get the net force and we're gonna apply it at that section. So the roof, the pressure at the roof is 0.79873, and that's the same as the pressure that's acting on top of the column. And then ground level is 1.056. So for the roof part, the area below, we're going to compute that, and then of course area above is 0. So the area above is this part, which is 0, and then the area below. So for this one here, I don't know if you can see it. Let's see, let's make it larger. So the area below is the length of this rafter times the thickness. So this area here. Times 0.322. So this is the net force that should be acting at the topmost of the rafter. So that's, and then for the top of the column, it's this area. So it's the same as this one previous. And then what that will be top of column, area above. And the area below is the half of the column plus the width of the column, which is 2.975 times 322.322. Two nine seven five. So these are the forces that we have to add for the roof, topmost roof, and then top of the column. Modify that. Since we'll be adding this manually, I'll add 0 here now. I just needed to put 1 here to get the pressure that it was acting. So for the roof along the y direction, it's 1.54. 1.54. Top of the roof is 3.57. So now we have the proper roof profile, or the proper wind force that's really acting on the structure. Further, I would like to
state that earlier I forgot to multiply this by 2. I also because of the symmetrical side. So what I'll do is actually I already multiplied this by 2. Earlier I did not. So these are the correct values that we were supposed to input. And also all you have to do is just go to the wind load along Y, modify it in here. I've already modified it. So just want to show you that I forgot to do that earlier. So moving on to still optimal design. What still optimal design is, what it simply means is it's the best or most effective. So the advantages are quicker analysis time. So what I mean by quicker analysis time is that the iterative process is much quicker. Instead of doing it manually, going to AutoCAD and uh, finding these sections, because of course if you have a bunch of sections, then uh, you would have to try to get the shapes from start node to end node, start node to end node. And if this was a long member with different nodes at intervals, then this takes time. So finding taper sections is more convenient. Yes, this is what I was talking about regarding if one continuous member has a lot of nodes in between, and if one end was 300 and the other end was 600, so if they had like 5 nodes, then trying to find the end of one node is quite difficult if you don't use AutoCAD. It also gives the most economical sections. And of course, if it gives economical sections lighter weight, then less base shear, which is good because earthquake is less of a factor in the structure. So my previous design, what I used to do is pretty much something like this. What I would do is I would measure it first, measure the distance of a member or between the nodes, and I would give an arbitrary section due to experience, say meaning for instance this one here, I would make the end 0.68 and at the topmost 0.29. Take note, this is all arbitrary and it would take an iterative process. So I'm just showing this is how I would do it. For the bottom part, these are the sections and inputs that I would use. Middle section and the top section. So here I'm showing you that this is the top section, bottom section, lower section. So as you can see that they all have the same section, and that's how I would do it with previous programs. And just imagine if this had a lot of nodes, a node here, another node here, another node here, then it would take you a lot of sections just to complete a perfect taper from the end part to the top part. And just imagine if after inputting that you run the analysis and you find that it was inadequate, then you'd have to do another iterative process, and then you'd have to edit all those sections again and then run again the analysis, see if it passes, and if it doesn't again, then you'd have to do it again, and so that's time consuming. So when using optimal design, all you have to do is pretty much what I do is I input an arbitrary section. For this section, the top section, I just put something like this. More section that's a little bit heavier so that it can find the section that's best suited. So pretty much the middle section is not really a great deal because what I'm trying to do is I'm trying to find the section needed here and the section needed here, and after that I will taper it. So how to use taper design, we have to go to the still design, then go here to the still optimal design, click that, and it will take us to a screen like this. With this screen, what we'll do is we'll select what we need to do an optimal design to, and then an iterative process that it will find which is best suited. Even if you put a large number amount of iterations here, and let's say if within 5 iterations MIDAS already found the most suitable, it will give you this notice, and that means it hasn't changed already, so it has found the most suitable sections. So as you can see here, this is the analysis done earlier, and as you can see, this is from the beginning to the 5th iteration, and even the I think sixth iteration. As you can see, it's already here. And so from the first to the last iteration, it's a lot of weight saved. The column or the raptor end actually got heavier on this part, but this part is very substantial. As you can see, there's 3 sections that were economized. But if you compare this much savings to this much savings, it's a great deal. So what we'll do is so as you can see, this is what I showed you in the slide. So this section here, so this is pretty much an arbitrary section that I put. Okay, what I'm going to do is I'm going to first run the analysis, and then I'm going to design. I'm going to still optimal design, and then I'm going to click all these sections except null. And then now this is options, and I will do 10 iterations. So now Jen is finding the most economical section, and it will go to an iteration process until it finds the most economical section, and it will give me a screen saying that it has found the most economical section. So after 4 iterations, it has already found it. So okay. You can get the graphic for here. So this is the one that I showed you earlier, this graph here. You can also see using other graphs. Close that, and then what I'll do is I will so I will update the model. So now this is the section that I will use for a tapered section. So now what I will do is I will make a raptor section. So you can go to section, add new section, and then put a section here. I've already made that section right here. So first let's see what this section is. So it's 0.8356. Let me check. 0.8356. Okay. 0.8356. 0.2092 for the width. Oh, IJ. And for the end section, I'm using the W1840, 0.45. And for the thickness of the web and thickness of the flange, what I will do is I will get the mid section, or I'll try to get them somewhere in between. As you can see, the sections here for the thickness of the web and the thickness of the flange differ. So what I'll put is just a ½ inch thickness of the web and the thickness of the flange. And I just call this raptor. So okay. So now what I'll do is I'll apply this raptor to the whole section. So let's drag and drop. And then after that, let's go to the presentation. So Jen found this section and for the raptor bottom and this section for the raptor top. And what I did was I combined those two sections together, the I node and the J node. I already know this, the end part of the I node was because I started, it's because this is I node, J node, and then for this section here, I node, J node, and so on and so forth. And so what I'll do now is I'll create a tapered section. I'll first create a left tapered section for this left side, and then I'll create a right tapered section for this side, for the right side. So I'll show you how it's done. And then what I'll do is I will member assignment, and I will tell Jen that this whole section is one whole section. So let me show you. Just gonna make into tapered group. So I'll call this left side, and then I'll select. The elements that to tapered, and then I will add. As you can see, Jen does it very simple and it just makes everything so it's a perfect taper. And then I'll make another group. Sign and this. And after that, I will make it into. So, like I said earlier, I will make these sections so that Jen knows that this whole section is one member. So, as you can see, this section here now it's one member there. There you go. So I can close that and you can run the analysis. So now I go to still design check, and let's see the demand capacity ratio. So as you can see, this section Raptor is failing by 70%. So let's check what is failing. So it's failing in combined. So what I'll do is I'll change some section first. I'll modify the section, and I will make this section 3 and this section 3. Okay. Then I will run the analysis again. Check. So there you go. The Raptor is passing. Actually, you can adjust it depending on how economical you want. For this section, let's see what it's failing in. So it's failing in slenderness. It's also failing in bending, combined bending also. So 13. Move up to the weight 18. Analysis. There, as you can see, it passes, but this star here, it's showing me the KL over R is failing. But anyways, for this section, it's these sections here. So they're going to be braced anyways. So that's not really a big factor. So see, it's failing. And only a small amount in the slenderness ratio. So as you can see, using the optimal design to design for your structure is very convenient, very fast, instead of manual iterations. So from the initial sections that I inputted for the uh, in Gen to the final section here, which I just changed this here a little bit, iteration from myself. Actually, just one time, and I was able to find an economical section. So also, what's good about Gen is, since this section is a built-up section, and we can find the weight of the plates that's already needed. So what we'll do is we'll go to bill of materials, and we'll check the bill of materials. And here, as you can see, it gives me the weight, so I can already order that, or have purchasing ordered, know the weight that we need for that plate if they need it. Also, painted area, it gives it already, and also gives the weight of the per member. So for tension on the elements, actually, the tension on the elements was not part of the original design. What happened was the contractor added turnbuckles for erection purposes, and what I wanted to do was check if what would these tension only elements cost, or how they help the member or the structure, or if they were good or bad. So I modeled it and I checked. So anyways, for tension only elements, they're generally used for modeling members that exert axial forces only, such as space trusses, cables, and diagonal members. But for using tension only elements in MIDAS Gen, it's you have to heed or be very careful on how you use it. It's due to the fact that tension and compression only elements can't take any bending or uniformly distributed load. So to do that, because even their own weight tends to since it's their own weight is distributed uniformly, it will cause bending. So what we must do is convert the self weight into nodal forces, and then after that the nodal forces to self weight. So let me show you how that is done. So in this model, I've already included the tension only elements, which are included here. As you can see, there are braces. So for these tension only elements, I used it was a 16 mm diameter, so which is this one. So what we must do first is to get the weight of the tension only elements. So what I do is I make a tension only element, and what we do is, since it's steel, we have the same properties, the modulus of elasticity, the Poisson's ratio, but the only thing is I put the weight density to 0, so that they won't include any self weight to the model. So after that, what I'm going to do is I'm going to select the whole structure, and I'm going to make this all tension only elements. It's just because this has 0 density, and then I will select the tension only elements, and I'll put steel material to them. Now what I'll do is I'll run this, and then I will go to mass summary table. Let's see, first let me check where are the nodes. So the tension only elements showing that it's from 500 to 515 are the nodes. So I can go here and I will check that this is the mass of those only tension only elements. So I'll copy this. Let me open also a Excel sheet. So what I did was I copied it and I pasted it on Excel sheet, and what I'm interested in is only this one. So what I'll do is I'll copy this and then I'll paste it in here. This is going to be the X, Y, and Z. I don't need this. I'll delete it. So going back to this, let's unlock it first. Okay, so for the Excel sheet, what I'm going to do is I'm going to copy this all. So on this side is the node numbers, and then this is our MX, MY, and MZ. So I'm going to copy this. And then I'm going to put this in nodal masses. And I'm going to paste right here. So here's the nodal masses in the MX, MY, and MZ direction. As you can see, they are applied now. So the next thing I must do is for those nodal masses to a nodal body force. So these nodal body force are going to be converted to a self-weight load case. So what I'm going to do is I'm going to select the nodes that I'm going to convert to a self-weight. And then nodal mass. And then take one scale factor. And then add. As you can see, now that the weight of the tensional elements are now converted to self-weight on the nodes. And then after doing that, I have to return the structure back to the normal materials. So, concrete, we'll go to concrete. So after completing that process, we also have to actually let me first continue the presentation. So before continuing, also we have to convert the load combinations to load cases to properly check analysis result. This is due to the fact that when we do a load combination, they are being additive, and so therefore the results are going to be wrong. So we have to convert the load combinations to a load case so that they can be acting properly on the model. So let me show you how that's done also. So we go to loads and then using load combinations. So I'm going to select all these load combinations and change still this Sign, then apply. So now all the load combinations are being converted to a load case. So now when we check for results, they will be properly what do we call that? Properly give the right results. So okay, now let's check. First, let me run the analysis. So the results. Then I'm going to check for forces. So let's first see the combinations of. So let's check this load combination here, which is, let's check one along Y. So 11. And then we'll see if any compression, it should be 0. So tension volume elements are not taking any forces. So as you can see, these are the forces on the load combination where the earthquake is going along X, or along Y, I'm sorry, along Y. And for compression, they take no compression. So pretty much you can just check and see if after that you can design for this tension over element. So thank you for listening. Hope this was informative.